Okay, it's a long title. I think, yeah, the only reason why I wrote such a long title is that most probably I won't be able then to talk about all these things. So at least they are in the title. Okay, so well, but let's start with symplectic capacities just to fix the notation. Well, you all know what is a normalized symplectic capacity. Here we're just really working just on the standard symplectic vector space, or CN with the standard symplectic form. And then we have our capacity, which is monotone with respect to inclusion, rescale quadratically, and it's normalized. Maybe here you can notice I've written the axioms of what is actually should be called I think McDuff and Salomon in their book, they call it an extrinsic symplectic capacity, because here the monotonicity is required only for symplectomorphism which are globally defined. Okay, so in some sense this is a weaker notion. Like for instance, the Hofer displacement energy would be a capacity in this setting, but it's not. If you ask more, so it's a weaker notion. The only reason why I'm using this is that all the results will hold also in this generality. So why not? But if you want, you can assume that this is just a usual capacity. Okay, so these are normalized symplectic capacities, and just again to fix notation, we have the smallest possible capacity, which is called ball capacity or Gromov width. No, it's you look at the biggest symplectic ball that you can, symplectically embed into your subset. And the cylindrical capacity, so you look at the smallest cylinder in which you can symplectically embed your set. And these are normalized capacities, and they are respectively the smaller and the biggest normalized capacities. And there is an old open question, namely, do all normalized capacity coincide on, let's say, bounded convex domains? I think this question goes back really to the 90s when the first capacities were defined, and maybe initially the motivation was that when symplectic capacities were defined, for instance, the Hofer-Zehnder capacities, Terbox capacity, and so on, people also took care of computing the capacity in particular examples. And then it turned out, let me write it here, it's here. Yes, that on so many of these normalized symplectic capacities actually coincide with the systole of the convex set. So here so if I have a convex set, let's say with smooth boundary, I will call systole the minimal action of a closed characteristic on the boundary. Now, as you know, so now the boundary is smooth, so it's a hypersurface in a symplectic manifold, in a symplectic vector space. So it has a characteristic line bundle, the kernel of the omega, and integral lines are called characteristics. And then we look at the actions of the integral of a primitive of omega over closed characteristic, and we take the minimal value. Okay, and it's a very classical result going back to Weinstein, that on convex domain you always have closed characteristic on the boundary, and we take the smallest action. And many of these capacity which are spectral, I mean that they agree with some action of some characteristic, they actually coincide with the systole. Okay, there are many results in this direction. I also with Jiangsu Kang, we also contributed to one of those. Okay, so this is in some sense some piece of evidence for a positive answer to this open conjecture, but for the two extremal capacities, instead, the ball capacity and the cylindrical capacity, instead, it's not known that they agree with the system, none of them. And another important motivation for this question is Viterbo's conjecture, which is now almost 25 years old. I wrote it here. So if I take a normalized symplectic capacity and X is a bounded convex domain, then the capacity of X to the power n should be bounded from above by n factorial times the volume of X, with the quality if and only if the interior of the convex body is symplectomorphic to a Euclidean ball. Okay, and this, of course, is related to the above question, because the inequality in Viterbo's conjecture holds trivially if you take the ball capacity or Gromov width, not just because if you can embed the ball, then your set has at least the volume of the ball, and if you write down, this gives us exactly this inequality for the Gromov width. So if you prove that all capacities coincide, a fortiori you prove that they coincide with the ball, and then you with the ball capacity, and then you prove Viterbo inequality. And that's why now in the recent literature, the coincidence of all symplectic capacities on convex set is also known as strong Viterbo conjecture. Okay, although strictly speaking, it implies only the inequality, but in Viterbo's conjecture, we have also this interesting characterization of the equality case. Okay, these are motivations, and let me now state a theorem. Well, let's say the statement is, oh, at the moment, I did something wrong. Okay. Yes, so this is a joint result together with Gabriele Benedetti and Oliver Edtmair. And actually, everything I'm saying today is a joint result. These are joint results with them, and the paper is on the archive since a couple of months. Okay, so short version, all normalized symplectic capacities coincide in a C2 neighborhood of the ball. Okay, so this means we now consider smooth domains with which are C2 close to the ball. You can imagine that what this means, the obvious thing. And then for this, all normalized symplectic capacities coincide. Okay, slightly longer statement. So if I have such a domain, C2 close to the ball, then I can find a globally defined symplectomorphism mapping this domain into the cylinder whose width is the systole of X. Okay, so this would tell us that the cylindrical capacity agrees with the systole. And then the second statement is I can also find a symplectomorphism, also globally defined, which maps now the ball, whose width is the systole, into X. Okay, so the second statement would tell us that the ball capacity agrees with the systole, and then of course you put these together, and the ball capacity and the cylindrical capacity agree, all the other ones are in between. And so this is the strong Viterbo conjecture in this C2 perturbative setting. And and then we can also say the equality case. So everything, so in this C2 perturbative case, everything one hopes to prove in general is actually true. We have the inequality, the Viterbo inequality, and the equality holds if and only if the convex body is symplectomorphic to a ball. Okay, so this is first, before I go on, are there questions about statement? Okay, then. So first observation, this C2 closeness is actually optimal. Here is the second thing that we can prove. We can find a sequence of domains, smooth domains, which converge C1 to the ball, and such that the ball capacity of this domain is strictly less than the systole. Okay, and then for other reasons, so the other inequality I wrote, the systole is less or equal than the cylindrical capacity, but this just follows from the fact that there exist spectral capacities. So the systole is less or equal than any spectral capacity, which is less or equal than CZ. So the inequality on the right is always true, and it's clear. The main point of the theorem is the first inequality. You can make the Gromov width strictly smaller than the systole for domains which are arbitrarily C1 close to the ball. Okay, so for these domains, capacities then do not agree. Okay, and then of course this fits also with the conjecture above, because now if I perturb it, so the ball is strictly convex, but so if I perturb it C2, it will stay convex, but if I perturb it C1, I can destroy convexity. So in some sense, this theorem is not disproving any conjecture. But it's just saying that our result is optimal. This C2 closeness is optimal. Okay, then the plan of the talk is to talk about proofs, but maybe before, let me just mention, previous results really in this direction. This, in some sense, is since these are optimal results, in some sense, is the final step of something that we started some years ago, trying to understand these questions around Viterbo near the ball. And so I should mention here, the first result is actually a result, now 6 years ago with Barney Braham, Umberto Niewicz, and Pedro Salomao. There we had proven the Viterbo conjecture for those capacities which coincide with the systole. And this was in domains, we were in C2, so in 4 dimensions, and domains which are C3 close to the ball. And here the proof was based on rep dynamics. We were looking at the dynamics on the boundary using global surface section to study the dynamics. We will see also global surface section now in this talk somehow. Then a second result is a more recent result with Gabriele Benedetti, where we basically extended the above, so again, the Viterbo conjecture, but now for domains which are C3 close to the ball, but in arbitrary dimension. Okay, if you go to arbitrary dimension, it's not clear anymore how to use global surface section effectively, and so we had to figure out something else. We did something else, and actually, I think I gave this my second talk at the Zoominar, and I gave a talk at the Zoominar really at the beginning of the Zoominar in 2020. And I talked about this result. So if you're interested in that, nothing, because the recording had a problem. So I think it's one of the few Zoominar talks for which there exists no recording. Okay, and then I should mention, another very recent result by Oliver Edtmair. He instead worked with a strong Viterbo conjecture, so he asked the equivalence of all normalized capacity, and he actually proved this in dimension 4, again for domains which are C3 close to the ball. Okay, but actually his proof shows also more, if you look just at the equivalence between the systole and the cylindrical capacity. it also shows that if you know that the systole is unknotted, then the systole agrees with the cylindrical capacity. So this is not a perturbative result. Now it's more general and holds generally for dynamically convex. Okay, and then there are of course many other results around the Viterbo conjecture. These are here focused only on, let's say, perturbative results. What happens when you perturb in some sense, the critical case of the ball, which is the equality case for Viterbo conjecture. Interestingly, the Viterbo inequality, and actually even the strong Viterbo conjecture holds, so equivalence of all capacities holds also for domains which are not convex, but which are very symmetric. Now, the results here are, for instance, for toric domain, or if you want, Reinhardt domains, under a certain monotonicity assumption. This is true. The strong Viterbo conjecture holds. This was proven by Jean-Gut, Vinicius Ramos, and Michael Hutchings first in dimension 4, and then now it's known also in every dimension. This is done Cristofaro Gardin and Richard Hind. Okay, so under strong symmetry assumption, you need convexity for this kind of results. And it's also interesting to notice that I saw, a few days ago, Michael Hutchings posted an interesting paper on the archive where he introduced zeta function for rib flows, and among other things, he shows that near the ball you can find domains which are not symplectomorphic to anything toric, at least toric star-shaped. Okay, because of course it's very difficult to say that something is not symplectomorphic to a large class of other sets. In particular, if you look at symplectomorphism only on the interior, and of course one could have hoped to prove Viterbo conjecture by proving that these toric domains are much more ubiquitous than when we thought, and in some sense this is true. There are also domains which do not look toric at all, but which were shown to be toric. But this result of Michael shows that you cannot get a whole neighborhood of the ball just with toric things. Okay, so let's go. I think it's time to prove something. Questions? Okay, then let's move to proofs. So here's the plan of the talk. I would like, first of all, to sketch the proof of the second theorem, so the counterexample, how to build something which is close, C1 close to the ball, but violates the strong Viterbo conjecture. And in the meanwhile, maybe I also sketch the proof, or maybe say just a few words about the equivalence between the systole and the cylindrical symplectic capacity. Okay, so part one, here the techniques are Hamiltonian dynamics, and through surface of section one reduces questions of red flows to, or actually our questions are questions about embedding to Hamiltonian dynamics. Then I would like to sketch the proof instead of the second part of theorem one, so the equivalence between the systole and the ball capacity. Okay, this is where other techniques are needed. We will see which. And then this second part is actually related to geodesics in the space of contact form with respect to a particular pseudo-metric, which is called Banach-Mazur pseudo-metric. If time permits, I'll also say something about this. But I'll decide to start with one also because, maybe many of you have heard other versions of this talk. For instance, I gave a talk about this in Lumini, where there was a big audience. And actually that talk is recorded and can be seen. And yeah, at that time, we had only preliminary results. So I basically talked only about 2 and 3. Actually, at the time, we couldn't even prove C2 close. The result was still C3 close. And okay, so just for completeness, this time I will start instead with the counterexamples. Okay, so we said we need a bit of Hamiltonian dynamics, and let me just fix some notation about very standard things in Hamiltonian dynamics. So compactly supported Hamiltonian diffeos, again, of our symplectic vector space. We take a compactly supported Hamiltonian on Cn, time-dependent and time-periodic. And then these are the convention I'm using for the Hamiltonian vector field. And then the Hamiltonian group is this group of time-one map of flows of such time-periodic Hamiltonian vector fields. And I'm denoting by A the action of a fixed point of a Hamiltonian diffeo. Okay, and as you know, this action doesn't depend on the choice of the Hamiltonian. You can generate the same Hamiltonian diffeo by several Hamiltonians, but the value of the action is always the same. And the other notion I need is the club invariant of the Hamiltonian diffeo, which is just you integrate, one possible definition at least, is you integrate the Hamiltonian both in space and in time. Okay, and this is also independent on the choice of the Hamiltonian, just depends on the Hamiltonian diffeomorphism, and it's actually a homomorphism to R on the space of Hamiltonian diffeomorphism. Okay, then we want to use Hamiltonian dynamics to construct embeddings, and for this we use, here is a useful symplectomorphism. Okay, you can also read the precise formulas, but that's not so relevant. So what we have here? We have this omega. This omega is a domain in R cross the circle cross C to the n-1. Okay, dimension 2n-1. And this is everything which is above some parabola. S is bigger than pi times w squared minus 1. S is the R variable, and w is the point in the Cn-1. Okay, so here, bottom left, you can see a scheme of what omega is. Omega is everything above this green thing. Okay, and then you look at this map, which is written just below the definition of omega. And this turns out to be a symplectomorphism. Okay, it's a symplectomorphism mapping omega onto C star cross Cn-1. Okay, so in other words, you see it from this thing. You know, the argument under the square root is strictly positive. So the first coordinate will never be 0. But apart from this, everything else you hit, and it's a symplectomorphism to this. Okay, and the other nice feature that it has is that it maps sublevels, let's say S less than S naught, here S is the first variable in omega, to balls. Okay, each sublevel goes to ball. So for instance, the sublevel S less or equal than 0 would be mapped to the unit ball, but the same holds for all sublevels. Of course, unit to balls minus this part where Z1 is 0. Okay, we have this symplectomorphism. And then we can just use this symplectomorphism to do the following. If now I have a Hamiltonian, again, time dependent, and now I'm looking at Hamiltonian in defined on a space of dimension 2n-2. So P cross, so circle cross Cn-1. And let's say it's supported in circle cross unit ball in this dimension. And let's say that this Hamiltonian has this inequality, which basically is just saying that the graph of our Hamiltonian is contained in the set omega I was referring to before. Okay, and then we can just associate to this Hamiltonian a domain in Cn where we just take the region, the sublevel of the Hamiltonian, so the triples STW, where S is strictly less than HTW, and we map through the other symplectomorphism to Cn. Okay, and then we add just the part which was missing, which was this the Z1 equals 0 intersected with the ball. Okay, so here in this picture I try to represent what this does. Okay, in this way you can basically parameterize all domains which near Z1 equals 0 agree with the ball. Okay, and then far away they're quite free. They should be just let's say transverse to a certain horizontal vector field. Okay, but for sure you get all domains which agree with the ball near this hyperplane Z1 equals 0, and once you have this, then you can go quite far from the ball. Okay, it's a way of representing domains with Hamiltonian. Okay, questions about this? Okay, if not, let's then see what we can say then in this case. Okay, and then it's easy to show certain things. For instance, we have a formula for the volume of this domain. The volume of this domain will be pi to the power n divided by n factorial. This is just the volume of the unit ball in that dimension 2n. And the correction is given precisely by the Calabi invariant. The other thing is that we have one-to-one correspondence between periodic points of phi and close characteristics on the boundary of that domain, let's say, other than those in this Z1 equals 0. When Z1 equals 0, we have all close characteristics, right? Because there the set was coinciding with the ball, so all characteristics there are close. But apart from all the other ones are in one-to-one correspondence to the periodic points of phi. And there's also a formula relating their action as close characteristic to their action as fixed points. And this is the formula. If this is a periodic point of period k, so a fixed point of phi to the k, then the action of the corresponding close characteristic is k times p plus the action with respect to the map phi k. Okay, so you pick up this kp every time. The action is small, as a fixed point, as a Reb orbit, it will have big action because of this kp. Okay, and yeah, then the last useful piece of information is that if you have a homotopy of these things, of this Hamiltonian, and if all these Hamiltonian have the same time one map, then actually all the domains that you obtain are all symplectomorphic. Okay, so in some sense, the symplectomorphism class of the domain you obtain just depends again on the time one map, not on the defining Hamiltonian, at least in this sense, if you really have a homotopy, otherwise it's a bit more delicate. Okay, how can we use then this to prove theorem 2, which I recall this was the counterexample. So we want to build a sequence of domains which converge C1 to the ball, but such that the Gromov width is strictly less than the system. Okay, the starting point is we take a Hamiltonian compactly supported, so time-dependent and compactly supporting the unit ball, dimension 2n minus 2. The properties are just that Calabi should be negative, but all fixed points should have action greater or equal than 0. Okay, such a thing is easy to get. For instance, here is one construction. you can take, start with a rotation or an element of UN, okay? But of course, you look at the whole isotopy from the identity in the positive direction, okay? And then, well, since we want to work with compactly supported Hamiltonian, you just dump it near the boundary of the ball just to slow it down, so it rotates less and less, and so that everything is compactly supported, okay? And let's say this is a positive rotation. So positive rotation would give us something with where Calabi is positive, and okay, the fixed point near the boundary will have action 0, but the fixed point at the center and the fixed point at the center will have positive action, okay, because it's a positive thing. So the action of fixed point is fine, but Calabi is positive. Now we want to make Calabi negative without messing with the condition of the fixed point should have non-negative action. We just take some set which is displaced, some open set which is displaced by our first map, and there we consider another Hamiltonian which is compactly supported in there, and it's very negative. Okay. Then when you compose these two diffeomorphisms, of course, since this thing is displaced, when you compose the two diffeomorphisms, you don't introduce any other any other fixed point. Okay, and you actually also don't change the action of those that you had because of, so the support is really a small ball, a small displaceable ball. So you haven't changed that, but since you have introduced the second Hamiltonian has maybe a very negative integral, then Calabi of the composition can be negative. Okay, this is how you build such a thing. Okay, once you have such a thing, you rescale it. Here is h lambda. You rescale by dividing w by lambda, and then you multiply your Hamiltonian by lambda squared. So this is the right rescaling. This rescaling has the property that the map mapping w to w over lambda, this conformally symplectic map, gives us a conjugacy between the flow of h lambda and the flow of h, but a real conjugacy in the sense that time is preserved. Okay? If you try other powers, you still get conjugacies, but then you are also changing time, the time parametrization. Instead, with these choice of powers, you preserve time. And of course, when lambda goes to 0, this h lambda converges to 0 in C1, but not in C2. If you take two derivatives, then you kill this nice coefficient lambda square in front of it. And but in C1 it's fine. So in particular, what you get is that this Hamiltonian for lambda small enough, this Hamiltonian h lambda will satisfy the assumption of the proposition before. The assumption was just that the graph of this Hamiltonian has to be above a certain parabola, but this is fine because this tends to 0. And then what else? If we look at the volume of the now we look at the corresponding domain. These will be our counterexample. Now what happens to these domains? Their volume, the volume of this domain, the volume, remember the formula was volume of the ball plus Calabi up to a constant, okay? And here Calabi is negative, so it means that the volume of all this domain is strictly smaller than the volume of the unit ball. Okay, all these Hamiltonian diffeos produced by h lambda, they have Calabi, which of course goes to 0, but they are all negative. It's lambda square, the Calabi of phi 1h. Okay, so volume is smaller than the volume of the ball, but the systole stays the same of the systole of the ball, namely pi, so the shortest periodic action. Here, the reason is just that for fixed point, so periodic points on the boundary of this domain, also periodic orbits or closed characteristics on the boundary of this domain are produced by periodic points of the corresponding Hamiltonian diffeo. Fixed points, by our construction, have non-negative action. So their action then as periodic points will be, because there the formula for fixed point was the period or the action of the Reb orbit is pi plus action of fixed point. Action is positive, so it's at least pi. Then you have to take care of also periodic points of higher period, but this you take care just by taking lambda small enough. Okay, so the systole stays, the volume becomes smaller, but then now you don't have enough room to put inside inside this domain a ball whose a ball of width equal to the systole. Okay, so in this way you get that the ball capacity is strictly less than the systole. This is how you construct counterexample. Question about this? Okay, so maybe something. So yeah, also the proof of the equivalence between the systole and the cylindrical capacity when a domain is C2 close to the ball uses similar techniques. It's a bit more involved. Now the logic is a bit different. Now the domain, we don't have to construct a domain. Now the domain is given. We want to modify it, so to push it inside a cylinder. But still, near its, we just have to modify it actually near its systole. And then we can again use the representation of domains that we have above, which is in a sense is a local representation of domains. Eventually, everything boils down to construct, so to modify the Hamiltonian of a given Hamiltonian diffeo by keeping the time one map, but choosing a better Hamiltonian, let's say. And this is something that you can do with standard techniques with generating function. This goes back to a paper of Bialy and Polterovich from the 90s, where they used it to construct quasi-autonomous Hamiltonian. Here we're doing something similar, this kind of techniques. Okay, now let's instead deal with the other results. So now we want to prove, so theorem 1, 2, which means we want to prove that if a domain is C2 close to the ball, then the systole agrees with the Gromov width, with the ball capacity. Okay, and in this case, it turns out that it's, again, we want to have a way of describing domains to work. Of course, it's always nicer to work on something which has structure of a vector space than geometric object. Before we used Hamiltonians, now we will use contact forms. Okay, and yeah, the way how contact forms on the sphere with the standard symplectic structure are related to domain is also very standard, just fixing the notation. Then denoting with lambda naught, the standard radial primitive of omega naught. Alpha naught will denote its restriction to the unit sphere. And psi star is the standard contact structure, so the kernel of this alpha naught. And then I'm looking at all contact forms defining this co-oriented contact structure, meaning so positive functions time alpha naught. I call this space F for forms. This is a space of contact forms. Okay, and as you know, every contact form here corresponds to a star-shaped domain, and yeah, the precise definition is this one. You use this function F power 1/2. So this is the domain. So in this correspondence, if you take constant multiples of alpha naught, these correspond to balls. And when you have inequalities, if a contact form is less or equal than another one, which of course means that the corresponding function in front of alpha naught is less or equal than the other one, then the corresponding domains are, there is the corresponding inclusion. And then there is, let me write it here, yes. I wrote it in this way. It's completely symmetric to just to have a statement as the one before. We have a vocabulary from going from contact form now to the properties of the domain. Okay, we have a formula of the volume, which I wrote, but which we won't use. We have a one-to-one correspondence between closed Rib-orbits of alpha and closed characteristics on the boundary of that domain. And in this one-to-one correspondence, period corresponds to action. And the other thing is that if I have a contactomorphism which is isotopic to the identity, and two contact forms, alpha and beta, are related by this, phi star beta is alpha, then I actually can find a symplectomorphism bringing my one domain to the other. Everything globally defined symplectomorphism doing this. Okay, and here is now that we have with this tool, this is now the strategy for proving the equivalence between the ball capacity and the systole. So we have our contact, so we have our domain. Our domain is C2 close to the ball. This means that the corresponding contact form is C2 close to alpha naught, the standard contact form defining the Hopf vibration of the ball. Okay, so our aim is to find a contactomorphism isotopic to the identity, this is phi, such that this holds. Phi star alpha is greater or equal than the quotient between systole of alpha and systole of alpha naught times alpha naught. Okay, so let's say we can do this. If we can do this, we have everything we need, no? Because the domain which is defined by alpha, this is our object we started with, is symplectomorphic to the domain defined by phi star alpha. Okay, it's property 3 of the proposition above. But by the inequality above, this is containing this other domain. But this other domain is a ball. Okay, if you look at really you look at the width, you have found a ball inside the domain defined by phi star alpha. So okay, instead of putting symplectically embedding a ball in our domain X, we have modified X by a symplectomorphism in such a way that it contains that ball. Of course, it's the same. Okay, so this will prove that the ball capacity is at least the systole, but then the other inequality is obvious, so we have equivalence. Okay, so the whole thing is to get this contactomorphism. The existence of this contactomorphism comes from this other, from actually a general result that we proved, which is this one, which has probably also, well, which has actually already some other applications. So here is the result. It's a sort of a, like, say, normal form for contact forms. ABE is always joint work with Gabriele, Benedetti, Oliver, Edtmair. So now we are in an arbitrary closed manifold with a oriented contact structure, and we take alpha naught contact form here, which is Zoll. By Zoll, I mean all Reb orbits are closed and have the same period. Okay, so then draws a free S1 action on our manifold. Okay, the statement is the following. If I find, so if I have alpha, another contact form, which is C2 close to alpha naught, then we can find a contactomorphism isotopic to the identity, which brings it, so phi star alpha will be f times alpha naught. Okay, it's a contact morphism, but the important thing is the property of f. F has the property that inside the set of its minimizer, so f minus 1 of minimum f, inside the set of its maximizer, there are invariant, there are sets, there are non-empty sets which are invariant under the red flow of alpha naught. In other words, there are periodic orbits of alpha naught, okay, inside these two sets. The theorem actually that you can read in our paper is actually a richer statement. This function f has some structure. It's a product of two functions, one of which is S1 invariant, and the other one is suitably small. And there is some reason why we wrote it this way, because this invariant function has also some nice feature. It's a sort of variational principle for detecting short orbits, but for our purpose, this simplified statement is good enough. Okay. The proof of this is, I must say, it's unfortunately rather involved. Yeah, it all comes from an old paper from Botkol. Botkol was a student of Moser, and in the 80s he was studying vector fields near, so perturbation of vector fields whose flow is completely periodic, and had proven some normal forms. And then with Gabriele, in this result of a couple of years ago I was mentioning before, we had already used this Botkol to prove another normal form, but which was less of a contact. We weren't building a contactomorphism. We were building a diffeomorphism, which was putting alpha in a certain normal form, which was good enough to prove the Viterbo conjecture. And this is how we proved the Viterbo conjecture, but not good enough to produce embeddings. And then also with Oliver, we started from there. So the proof of this theorem actually keeps as input the older theorem with Gabriele, and then with some Moser argument we end up here. And it's a bit also the difficult thing is try to keep the closeness at a minimum, and we actually managed to do it with C2 closeness, which is optimal also for this theorem, because yes, if you would, this is not true for C1 close, because otherwise you would violate, well, because of our counterexample. So in a sense, the theorem is optimal, but the proof, maybe it's not. It would be nicer to find another proof. This theorem, in a sense, is similar, and we'll see this in a little bit why. It's analogous to the existence of quasi-autonomous Hamiltonians. The existence of quasi-Hamiltonians is a relatively simple thing that you prove using generating functions, and here instead we don't have a simple proof like that one. Okay, but in any case, there is a proof, so you can use it. And now that we have this, we can achieve the goal I said before. So we now apply this theorem to the case of the standard Zoll contact form on the sphere. Now we take our alpha is C2 close to alpha naught. So we have our phi. And the first consequence, so now we get, by this theorem, if we look at this region where f achieves its minimum, okay, this contains a Reb orbit of alpha naught, but where f achieves its minimum, its differential is 0. And when the differential is 0, it means that the Reb vector field of alpha naught and the Reb vector field of phi star alpha are parallel. If you write the equation for where the Reb vector field takes value in, you have to differentiate, and when the differential is 0, the two vector fields are parallel, which means that these periodic orbit of alpha naught is also a periodic orbit of phi star alpha. Okay, and then if you look, so you found a periodic orbit of phi star alpha, and if you look at the action, you get that the action of this periodic orbit will be exactly systole of alpha naught times the minimum of this function. And so alpha has a periodic orbit with precisely this action. So the systole is in particular is less or equal than this number. This is the first inequality which I wrote. And then okay, below you have just this inequality just because any function is bigger than the minimum. And then you apply the other inequality above and you get exactly what you want. But phi star alpha is greater or equal than this ratio between the systoles and alpha naught. Okay, this was our goal. This proves also the other theorem. Questions about this proof? Okay, if not, then I think I still have 5-6 minutes. It's a 1 hour talk, right? Yeah.
That's correct. That's
okay.
Correct.
Okay. So still have 6 minutes. Then I have also time to tell you something about this relationship with this Banach-Mazur pseudometrics. Okay. So this Banach-Mazur pseudometrics, the definition was first suggested by Jaron Osterwald and Leonid Polterovich, and they were in writing appearing papers of Rosen-Zhang, Stosplievich, Zhang, Asher, and actually there was also a talk here at the Zoominar by Julien Dardenne, who explained how this Banach-Mazur pseudometric, the diameter of the space of dynamically convex contact form with respect to this Banach-Mazur pseudometrics. Okay, here is a definition. This is a pseudometric on the space of contact forms on a given co-oriented contact manifold. To the distance between alpha and beta, you try to minimize the oscillation of f, where f is the logarithm of the conformal factor. When you try, so you move beta by all possible contactomorphism isotopic to the identity, and you try to, this will modify the conformal factor between beta and alpha, and you try to minimize the oscillation of the conformal factor. In other definitions, you sometimes try to instead to minimize the subnorm. There's just little change in what you get. I prefer to do it with the oscillation. Okay, this is a pseudometric on the space of contact forms. And of course, it's a pseudometric because, for instance, if I just alpha will have 0 distance from everything in its orbit. So I can apply a contactomorphism, or I can also rescale by multiplying by a number and still get 0 distance basically by definition. But actually, even if you quotient this out, this stays a pseudometric, even on the quotient. Okay, but nevertheless, it's an interesting object. And here is a first, actually, this is an easy thing to prove. So let's look at this definition. So the first thing is that if the infimum on the definition of this pseudometric is achieved, let's say by some f and some phi, first thing, there exists a probability measure which is invariant under both Reb flows of alpha and of phi star beta, and is supported in, let's say, the set of minimizers of f. Okay? And there is then another one which is also supporting the set of maximizers of f. Okay? So the two Reb flows share a common invariant probability measure. Okay? This is proved actually by contradiction. if this is not the case, then there must be a Lyapunov function. Well, there must be a function defined on the manifold, which is Lyapunov for the flow of one of them on the set, and then you use this to modify, to show that then this f was actually not optimal. And then the optimal f, the other thing is that you can use this to really construct a minimizing cross geodesic from alpha to beta. So you have this minimizing cross geodesic under this very strong assumption that the infimum is achieved. So this assumption is, of course, very strong because it has very strong consequences. So in general, you cannot hope this infimum to be achieved. However, it is achieved, let's say, if you don't go too far from a Zoll metric. And here is the theorem that we can prove. If alpha is C2 close to a Zoll contact form, then the infimum in the definition of the Banach-Mazur distance is indeed achieved. Okay, so in particular, you can connect a Zoll contact form with any other contact form which is C2 closed by a minimizing geodesic, and you can also say exactly what is the Banach-Mazur distance between alpha and alpha naught. The Banach-Mazur distance turns out to be the logarithm of the ratio between Tmax and Tmin alpha. So here, Tmax and Tmin alpha are the maximum and the minimum period of the short closed Rib orbits. So Tmin is just a systole of alpha. So it's really the shortest period of periodic orbits. Tmax is, no, here we are perturbing Zoll contact form. So at first everything was periodic orbits, everything was periodic. When you perturb such a situation, what you obtain, just general things about vector fields, you will obtain a bunch of periodic orbits whose period is close to the period they had with respect to alpha naught. And then, of course, many other periodic orbits, but of, let's say, very, very long period, huge period. Okay, so I call short orbits those which are instead here bifurcating from the smallest period, and this Tmax is the maximum then. So we have also a precise formula for this thing. Okay, so in some sense, this builds a bit a bridge between this Viterbo conjecture, if you want, between systolic inequality and this geometry in this Banach-Mazur geometry. And by the theorem I stated before, of course, if one could prove that the contact form which is defined by a convex body can be joined to the standard contact form by a minimizing geodesic of this kind, or in other words, if this infimum exists, then this would imply the Viterbo conjecture, actually even the stronger statements. But of course, the theorems we have for now about existence of these minimizing geodesics are instead just local, but still we find it interesting to notice this, the fact that this consequence would hold instead also global. Okay, I think, yes, this is what I wanted to tell you. Yeah, thank you very much for your attention.
Okay, let's thank Alberto again. Questions for Alberto?
Maybe I'll stop share. You can also see me.
May I ask you a question? So concerning geodesics, so is there a way to describe length structure and to write geodesic equation, kind of?
Yes.
So analog of quasi-autonomous condition. Did you try to do something like this?
Yeah, no, we are still missing one ingredient to do this. In a sense, we have some, let's say, when this infimum is achieved, we can describe some minimizing geodesics. but we still don't know exactly. We don't have a full characterization of minimizing geodesic. If I have a minimizing geodesic, it's not like I can not like in the case of the Hofer metric when I can say, okay, yes, it's produced by a quasi-autonomous thing.
No, but my question was slightly different. So I want to split the question in two. So first, what is geodesic? And so then what is conjugate point? And then minimizing geodesic, for instance, could be geodesic without conjugate points or something like this. So instead of right away describing minimizing geodesic, so like variational definition, yeah. So
we're also lacking, I think, a variational definition of also of all geodesics, not only minimizing ones.
I see.
But this is this is something we should try to understand better.
Cool, thank you.
I have a question. Hi, Alberto. I have a question about theorem 5. I didn't completely understand what Tmax and T means. So my guess would be that Tmax would be the nth. If you're in the, if you have a domain in R2n, it would be the nth Eckland-Hofer capacity. Is that correct?
Yes, exactly. So yes. It's so in this case it would be exactly the nth Eckland-Hofer capacity. Yes, precisely.
Oh. Nice.
Yes, but here, this was just a definition. It was defined as Tmax. In this perturbative case, we can just define it like this by looking at periods. But in general, it would be exactly the nth. And in fact, since this theorem is all symmetric, we also get a sort of inequality also for the nth Eckland-Hofer capacity.
Okay, but so you expect you expect the theorem to hold in general, not with the without this C2 approximation somehow, or not?
It would be nice if it would hold for all convex.
Okay.
Of course, if we do, but if this holds for all convex, then Gromov width of also ball capacity equals system. So it has a strong.
But because you have two statements. One, you have the fact that the minimum is achieved, and then you get an inequality. So you could have, of course, the inequality without having the minimum achieved. Which is maybe a little bit easier. Or more likely.
But concerning this n capacity, the other result that one gets instead. So everything. In all the proofs today, I was always looking at the minimizers of f of this function. If you look at the minimizer, you get also a statement about uniqueness of things which are normalized as the nth Eckland-Hofer capacity near the ball.
Okay.
But then this turns out to be really so near the ball. Jean Gut and Vinicius Ramos have found also examples where instead this does not hold. This axiom which should characterize this nth capacity instead, if you go far away from the ball, but even staying convex, they do not hold.
Okay, thank you.
Any other quick questions? So we will have more time for discussion, but I just want to stop recording. Any other quick questions before we do that?